On the night of July 21st, 2025, a faint streak of light crossed the field of Hubble's eye. It wasn't remarkable at first glance, just another visitor of dust and ice wandering through sunlight. But when the image was processed, something was wrong. The tail, that shimmering thread meant to stream away from the sun, was instead pointing toward it. Against all intuition, against everything we've come to expect from the dance of radiation and dust, the light was reversed. Astronomers double-checked the coordinates. They reprocessed the frames. They looked for an error, a reflection, a cosmic ray, a trick of the background stars, but the pattern held. In that single image, the geometry of nature seemed to fold in on itself. Weeks later, when another telescope looked again, the Nordic optical, under the cold skies of La Palma, the tail had changed direction once more, this time obeying the old rule: flee the Sunday. And so began the whisper in observatories around the world: what could turn a comet's breath against the light that made it? You see, the universe doesn't often contradict itself. But when it does, it invites us to listen closer, to ask whether what we're seeing is illusion or revelation. And tonight, we embark on a new journey, where the theme of the new official 3I Atlas images are hard to believe, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map tonight? Tell me where in the world you are and what time it is as you listen to this. It's always fascinating to see who's joining us from all around the world. On July 21st, 2025, the Hubble Space Telescope captured something quietly astonishing. Against the black canvas of interstellar space, a streak of light appeared to turn its face toward the sun instead of away from it. The comet known as 3I Atlas, our third confirmed interstellar visitor, showed a plume of material streaming sunward, as though the star's gravity was not pulling it but somehow provoking a defiance. Weeks later, the Nordic Optical Telescope in the Canary Islands took another series of images. The tail had flipped. Now it pointed in the direction everyone expected, pushed back by the relentless pressure of sunlight. To anyone who studies comets, this reversal was more than curious. It was revolutionary. Comet tails do not simply change their minds. When we speak of a comet's tail, we imagine something passive, something sculpted by light. Dust and gas released from the nucleus drift outward, caught in the solar wind, tracing a beautiful arc that always, without exception, points away from the Sunday. The physics is elegant, simple, and remarkably consistent. So, when an object does the opposite, when it appears to defy the very radiation that defines it, we must stop and ask what the universe is trying to tell us. The Hubble image that morning was more than a picture. It was a question mark written across the void. At first, astronomers hesitated to call it an anomaly. Space is full of tricks. Perspective can deceive even the most disciplined observer. Perhaps, some suggested, we were seeing an illusion of geometry, a projection of dust crossing our line of sight, creating what looked like an anti-tail. And yet, the timing, the symmetry, the crispness of that beam toward the sun did not fit the models. The orbit of 3I Atlas was steep, slicing through the plane of the solar system, and the Sun-Earth comet alignment at that date should not have produced a strong apparent reversal. Still, scientists held their breath and waited. Then came the second image from the Nordic telescope, and with it, the realization that whatever was happening was real, dynamic, and physical. The direction of emission had changed. The comet had truly turned its jets around. To appreciate the magnitude of this discovery, you have to imagine what 3I Atlas is. It is not a regular comet born from our own sun's debris field. It is an exile from another star system, a fragment of ice and dust that has drifted for millions, perhaps billions of years through the interstellar medium, until, by pure accident, it entered our celestial neighborhood. It carries with it the chemical fingerprints of a distant world, a story of another sun. When such an object behaves in a way no comet ever has, we are, in a sense, watching the laws of another solar system write themselves across our sky. The Hubble team analyzed the data again. The antitail appeared sharp, linear, not diffuse. It suggested directed emission, a narrow jet, rather than a broad scattering of particles. If this had been a simple projection, the gradient of brightness would have matched known scattering functions for dust. But the spectrum hinted at something else. There was an enhancement in carbon dioxide lines, a signature typical of sublimating ice, but with a ratio that was far too strong for its heliocentric distance. CO2 shouldn't dominate. At this range, unless the surface was unusually rich in it, or something had disturbed the balance of active regions. The Nordic telescope's follow-up, taken in late August 2025, told another chapter of the story. The tail had resumed its usual orientation, pointing directly away from the Sunday. The comet's coma brightened by a factor of nearly 2, and the spectrum showed a growing presence of water vapor. It was as if a second layer beneath the CO2 crust had awakened, a buried ocean of ice coming to life as the comet drew closer to the Sunday. This transition from a CO2 dominant to an H2O dominant phase could, in principle, create forces strong enough to alter the visible direction of ejection. But the symmetry was still too perfect, the reversal too clean, almost mechanical. In the quiet rooms of observatories from Hawaii to La Palma, discussions grew intense. Could this be the signature of jet inversion? That term jet inversion sounds dramatic, but it simply means that the direction of outgassing flips, possibly because the comet's rotation exposes different active areas over time. Yet the period between the two observations was weeks, not hours, suggesting a large-scale reconfiguration rather than a mere spin-induced change. If the nucleus was rotating every few hours, we should have seen repeated variations in brightness. But the light curve was strangely stable. Something deeper was unfolding. Some astronomers began reconstructing the geometry. They modeled the position of the Earth, the Sun, and the comet for each observation date, simulating how a sheet of dust might appear from different angles. They accounted for the tilt of the orbital plane, the phase angle of illumination, the forward scattering of sunlight by small particles. Still, the models failed to reproduce the exact symmetry of the first antitail. The light was too concentrated, the direction too precise. It seemed less like an optical illusion and more like intent. Of course, nature can be wonderfully deceptive. In the past, we've seen comets split in two, release asymmetric plumes, or exhibit complex dust shells that mimic artificial geometry. Halley did it, Hale-Bopp did it. Yet 3I Atlas was not simply another dusty wanderer. Its velocity, its composition, its trajectory, all whispered of an origin beyond the sun's domain. The interstellar medium it traversed for millennia might have sculpted its surface in ways we do not yet understand. Cosmic rays, interstellar dust impacts, and collisions with micrometeorites could have carved cavities, channels, or sealed vents that now erupt as sunlight warms them. Each burst of activity could behave like a thruster, altering not just the appearance, but the motion of the comet itself. If that were the case, one might expect to detect a non-gravitational acceleration, an almost imperceptible deviation from its calculated orbit. After all, if jets are firing asymmetrically, they impart momentum. Yet when the orbital solutions were refined, the trajectory still matched a purely gravitational path within measurement error. That paradox deepened the mystery. Either the comet's mass was enormous, so the thrusts had little effect, or the jets were arranged in a near-perfect balance, cancelling one another out. Both possibilities challenged our intuition. The Hubble team considered another factor, the size distribution of the dust grains. Small grains, a few micrometers across, responds strongly to radiation pressure, and can appear to move in unexpected directions. Larger particles, however, are too heavy for light to push. If the antitail were composed mostly of large grains released earlier and now catching the sun's rays at a particular angle, that might explain the reversal. But again, the morphology did not fit the timeline. The grains would have dispersed, forming a broader fan, not a thin, deliberate streak. In science, we often stand on the boundary between pattern and coincidence. The danger lies in seeing intention where there is only complexity, and yet there are moments when data persistently refuse to fit within our known frameworks. 3. Atlas was beginning to look like one of those moments. The reversal was not an isolated quirk, but a signpost of a deeper process, one that might reveal new physics of sublimation, or perhaps, more unsettlingly, a design. You see, when something crosses interstellar space to reach us, it carries the fingerprint of its creation. The question is not merely what 3I Atlas is doing, but why. What conditions could produce an object that vents toward the sun, pauses, and then reverses? Could a layered structure, CO2 above, water ice below, produce such a shift as thermal waves move inward? Possibly. Could a complex rotation, with jets on opposing hemispheres, create alternating patterns of emission? Perhaps. Could it be something else entirely? Something not driven by chance but by purpose? That is a question no scientist should leap toward, but also one we should not be afraid to ask when the evidence demands it. For now, the data suggest a sequence of physical transitions. Early in July, as sunlight began to warm the outer layers, the CO2 ice sublimated first, producing jets that blew toward the Sunday. As the comet moved inward, temperatures rose, igniting the deeper water ice regions, which released stronger plumes in the opposite direction. This natural inversion could mimic what looks like control. Yet, the precision, the timing, the balance of forces, these are the details that separate coincidence from control. And that, perhaps, is why the new images are so unsettling. They hint at a choreography in the vacuum, a dance that follows rules we have not yet written down. Astronomers have long known that comets are storytellers. Each one carries the memory of its birth, the temperature of the nebula, the ratio of volatiles, the violence of collisions that shaped it. But interstellar, comets are more than storytellers, they are messages from other suns. 3I Atlas speaks in the language of light and gas, and if we listen carefully, we may hear how other worlds evolve, how other skies form their comets, how universal the laws of physics truly are. The two images that change the game remind us that discovery often begins not with understanding, but with confusion. The universe loves to surprise us. And so, as the scientific community gathered to compare data, a new kind of curiosity took shape. Could geometry alone explain the reversal, or had we witnessed a genuine physical phenomenon? The next step was clear. We would have to test the illusion by reconstructing the celestial geometry, the shifting triangle between the Earth, the Sun, and 3I Atlas. We might discover whether the antitail was simply a trick of perspective or the first sign of something far more extraordinary. The story of 3I Atlas, then, does not end with the two images that startled us. It begins there. For what follows is a journey into the heart of celestial geometry, into the delicate play between light, shadow, and the observer's eye. Perhaps the cosmos was showing us not defiance, but perspective. Or perhaps, in that narrow streak of light pointing back at the sun, it was hinting that even in the vast quiet of space, there are still secrets waiting to turn and look back at us. And to understand that, we must first learn to see not only what is before us, but how we are looking at it. As Earth turned and the observatories prepared for their next exposure, the debate over the antitail of 3I Atlas deepened. The first chapter had left the world staring at two conflicting portraits of the same traveller, one looking defiantly toward the sun, and another falling back into expected obedience. To move forward, Astronomers had to peel away illusion from reality to ask not what they thought they saw, but what geometry itself was whispering through light. You see, in the vastness of space, our eyes are never neutral. Every image we take is filtered through alignment, distance, and the delicate ballet between sun, earth, and object. A comet's tail is not a flat ribbon, but a three-dimensional stream, a river of gas and dust stretching for millions of kilometers through invisible currents of solar radiation. When such a structure is seen from different vantage points, what looks like reversal might be nothing more than the bending of perspective. In celestial mechanics, geometry is the first illusion maker. So the teams began their reconstructions. They fed coordinates of July 21st, 2025 into their simulators, plotting the position of the Hubble Space Telescope against the line of the Sun and 3I Atlas. Then they advanced the model to late August, when the Nordic Optical Telescope took its picture. The orbits were transformed into luminous threads in a digital sky, showing how the comet sliced through the ecliptic plane at a sharp angle, about 70 degrees. In such an orientation, the sheet of dust that fans out behind the comet could, under certain lighting, seem to swing forward. But even then, the illusion would require perfect timing and an extraordinarily flat plane of emission. Hubble's image showed a razor-thin sunward beam, not the kind of diffuse fan expected from a projection effect. The Sun-Comet-Earth phase angle was small, around 15 degrees, which should have produced a gentle brightening near the nucleus, not a collimated spike of light. The data hinted at genuine emission, not an optical trick. Yet astronomy, cautious as ever, refused to jump to conclusion. Nature delights in disguises, and so every hypothesis had to survive the light of mathematics. By mapping the orbital geometry day by day, the researchers found that an apparent anti-tail could indeed form if the Earth crossed the plane of dust that trails the comet. As we moved through this invisible sheet, the perspective could cause the stream to appear as if it were pointing toward the Sun, when in fact we were looking along its edge. It was like watching a veil turn translucent under a shifting light. The particles themselves had not changed direction, only our position had. It was a comforting explanation, one that preserved the sanity of physics, but it did not fit perfectly. The anti-tail in Hubble's photograph was too bright, too narrow, and appeared too early in the geometry timeline. The crossing of the dust plane should have occurred days later. Something else, something internal to the comet, seemed to be at work. Still, to prove that, one needed to rule out geometry completely. So they turned to the color data. If the feature were simply a line of sight projection, its spectral profile would match that of the surrounding coma. But the sunward streak showed an excess in near-infrared reflectance, consistent with fresh CO, two frost particles larger and more reflective than typical water ice dust. That chemical signature hinted at active emission, gas dragging dust directly toward the Sunday. The geometry had contributed, yes, but it was amplifying a real, physical jet. One astronomer described it poetically. The sky is not lying to us. It is simply holding a mirror, and in that mirror, the comet is showing both its surface and our angle. The phrase, stuck. The problem was not in the data, but in the way perspective tangled with physics. To separate one from the other, they built 3D models of dust dynamics under the exact solar radiation conditions of July. Each grain of dust was assigned a parameter, its size, mass, composition, and the beta factor that defines how strongly sunlight pushes it. Then, through computational simulation, they watched how streams evolved under different emission angles. Only one configuration recreated both the sunward feature and the later reversal. A comet ejecting dust in two opposite directions, one briefly facing the sun and another, emerging later from the shaded hemisphere. That discovery led to a subtle insight. The illusion was real, but it was built atop a truth. The geometry had turned an already complex event into something astonishing. Light, angle, and physics had woven together like layers of music, each amplifying the other's resonance. What we saw was not deceit, it was harmony misunderstood. And yet, even this elegant explanation carried its own unease. The energy required to produce such directional jets was immense. For the comet to vent toward the Sun, the material must have been under internal pressure, stored in cavities sealed by time. When the sunlight reached the threshold depth, the gas erupted through the weakest point, hurling particles into the solar glare. As the nucleus rotated or rebalanced, those vents shut, and new ones opened on the opposite side. The inversion we observed was therefore both real and apparent, born of internal structure and revealed by cosmic alignment. But that still left the most haunting question. Why did the timing line up so perfectly with the geometry change as seen from Earth? Was it coincidence, or was there an unknown synchronization between rotation, illumination, and observation? In planetary science, coincidences that precise often signal hidden mechanisms. Perhaps the comet's spin axis was oriented in such a way that each major vent fired when it faced the Sun at just the right moment to create the illusion of a deliberate reversal. Or perhaps, in a more daring thought, something inside the object was regulating its outgassing cycles in a rhythm far too orderly for a frozen relic. In truth, astronomy has always been a conversation between humility and wonder. For every mystery, there is a temptation to ascribe design where chaos reigns, but the opposite can also be true, to dismiss coherence as accident. Geometry is the bridge that keeps us honest. It reminds us that the cosmos does not revolve around our perception, and, yet, it occasionally aligns so perfectly that it feels as though it does. As the simulations grew more refined, a curious pattern emerged. The models that best fit both Hubble's and Nordic's images were those in which the comet's orbital plane was slightly tilted relative to its rotation axis by about 20 degrees. This meant that during July, Earth's line of sight lay almost directly along the outflow plane, exaggerating any forward-directed emission. By August, that angle had shifted enough for us to view the same emission from the side, transforming what once looked sunward into a conventional tail. Perspective alone could not create the event, but it could dramatize it beyond recognition. The anti-tail was both illusion and revelation. Such dualities fascinate astronomers because they mirror the universe itself. Light reaches us only after a long journey, bent and filtered by gravity, time, and dust. Every image is a translation, every measurement a story told in a dialect of photons. In studying geometry, we are not merely calculating, we are learning how to listen to the silence between the stars. The anti-tail of 3i Atlas became a lesson in humility, proof that even the most advanced telescopes can be tricked by the cosmos's elegance. Still, the faint unease persisted. If geometry alone could explain the phenomenon, why did the spectral data change between the two observations? Why did CO2 fade just as H2O rose, in perfect synchrony with the tail's reversal? The transition seemed orchestrated, not random. It was as if the comet itself were responding to sunlight in a staged sequence, each act triggered by an internal clock. That clock, scientists realized, was thermal depth. The sun's heat, delayed as it sank deeper into the surface, reached the subsurface ice with precise timing, igniting a second wave of outgassing. The geometry merely framed the performance. The true actor was physics, and yet there was beauty in that precision. Nature, once again, had written poetry with mathematics. The illusion of a sunward tail had been born at the intersection of three motions: the comet's rotation, Earth's orbit, and the gradual propagation of heat beneath an alien crust. Three rhythms converging for a fleeting moment, producing an image that defied intuition. The Hubble camera had captured not just a comet but the choreography of time and light. As word spread through the astronomical community, the debate cooled into quiet admiration. Geometry had not betrayed us. It had revealed how delicate perception can be when stretched across cosmic distances. The anti-tail, though perplexing, was no longer heretical. It was a signpost, a reminder that the universe's simplicity is often hidden inside complexity. Still, the scientists knew their work was far from done, for if geometry could deceive so convincingly, what of the next mystery? What if another force, less visible, was shaping the comet's behavior, or something within the dust and gas itself, a mechanism of propulsion or balance we had yet to define? In that question lay the path to the next investigation. To move beyond illusion, one had to study motion. The reversal of the tale had shown that light could sculpt perception, but the next chapter would reveal how matter responds to that light, the subtle push and pull between outgassing jets and the comet's own inertia. The stage was set for a deeper exploration into the heart of reactive forces, where sublimation becomes propulsion and geometry yields to dynamics. And so, as the models rendered their last frames, the scientists prepared for a new kind of analysis. They would turn their gaze from the shape of light to the motion of mass, from perspective to momentum. For in the quiet expanse where dust meets sunlight, the truth of 3I Atlas was still waiting to emerge, not in how it looked, but in how it moved. And that is where the next chapter begins. Now that geometry had revealed its limits, the investigation turned toward motion, the quiet language of forces that act unseen. For a comet, motion is never a simple journey. It is a dialogue between sunlight and ice, between sublimation and recoil. Every molecule that escapes from its surface carries momentum, and every burst of gas or dust, however faint, delivers a push in the opposite direction. It is this subtle exchange that makes comets drift from their calculated paths, tracing arcs that no purely gravitational model can predict. But with 3I Atlas, the drift was nowhere to be found. When the new orbital solutions arrived, astronomers compared the data to the models that described its gravitational path. The fit was immaculate. Within the margin of error, the object followed a trajectory shaped only by the sun's gravity. No measurable non-gravitational acceleration appeared in the residuals. This was astonishing, almost paradoxical. The images clearly showed active jets, plumes of gas, and shifting tails, all signs of vigorous sublimation. Yet the orbit itself was unperturbed, as if the object were a silent stone carried by celestial mechanics alone. Something did not add up. To understand this tension, one must step into the physics of reaction dynamics. Every particle that leaves a comet's surface exerts a minute thrust on the nucleus. The total of those microscopic thrusts forms what physicists call a non-gravitational force. When strong enough, it bends the orbit, sometimes by thousands of kilometers over months. Halley's comet, for instance, shifts perceptibly after each perihelion passage because of asymmetric outgassing. But for 3I Atlas, an interstellar body streaking through the solar system for the first and only time, no such deviation was seen. Either the mass was immense, dwarfing the effect of any venting, or the outgassing was arranged in such perfect balance that all forces cancelled out. Both explanations strained belief in different ways. The first possibility suggested that 3I Atlas was unusually massive. If its nucleus were several kilometers wide with a density higher than water ice, then its inertia could easily suppress measurable acceleration. Yet the brightness data argued against such bulk. The total luminosity, even corrected for distance and albedo, implied a relatively small active area, perhaps 1 or 2 square kilometers at most. That scale could not support a mass large enough to nullify all recoil. The other explanation, near perfect symmetry, felt equally improbable. Nature rarely engineers perfection. Cometary surfaces are chaotic, pitted, irregular worlds where sunlight and shadow carve unpredictable shapes of ice. To produce zero net thrust, the outflow would have to be evenly distributed in all directions, like a cosmic breathing with no preferred side. That was difficult to imagine for a fragment from another star. A third path opened. Perhaps the acceleration existed but was hidden within the limits of our measurement precision. The velocity of dust, the speed of gas, the calibration of reference stars all carried small uncertainties. If the non-gravitational term were weaker than those uncertainties, it would vanish in the noise. To test that, the team constructed sensitivity curves, estimating what level of thrust would be detectable given the temporal resolution of positional data. The result was revealing. Any acceleration smaller than 10 millionths of a meter per second squared would fall below detection. In theory, that could allow for moderate outgassing without betraying itself. But to maintain such a delicate equilibrium over months was statistically unlikely. Still, physics often hides within the improbable. So researchers turned to models of reactive thrust based on sublimation rates. They took the observed brightness, the measure of sunlight reflected and re-emitted by the coma, and converted it into mass loss per second. Using standard sublimation laws for CO2 and H2O at the comet's distance, they estimated the flux of escaping gas. Then they multiplied that by the average exhaust velocity, roughly several hundred meters per second, to derive total momentum flux. Dividing that by an assumed mass of the nucleus produced a predicted acceleration. The numbers were small, but not negligible, far larger than zero. Yet reality gave them nothing. The object sailed through space with mathematical obedience, betraying no hint of push or pull. That silence led to a radical thought. Maybe 3I Atlas was not one body but many, a cluster of fragments whose collective outgassing averaged out. If small pieces vented in different directions, their individual impulses could cancel when viewed as a whole. Some comets, like 73P Schwarzmann-Wachmann, behave this way after fragmentation. But Hubble's images showed no clear evidence of multiple nuclei. The central condensation remained tight, with no resolved companions. And the light curve was smooth, lacking the flickers typical of fragment rotation. The unity of the object seemed intact. Perhaps, then, the explanation lay in the microphysics of its surface. Outgassing is not always free. Sometimes it occurs beneath translucent layers, causing trapped gas to escape through diffuse pores rather than jets. In that case, the momentum carried by escaping molecules is randomized, producing minimal net thrust. A crust of sintered dust and ice, hardened by cosmic rays during its long interstellar voyage, could serve as such a dampening shell. As the sun's heat seeped in, it would trigger slow diffusion rather than violent eruptions. The visual display of the coma would remain bright, but the physical push would fade into insignificance. If true, this would make 3I Atlas a kind of hybrid between a comet and an asteroid, a world active in appearance but inert in motion. It would also explain why its tail seemed to change without altering its path. The physics of sublimation could be playing out. Beneath a skin of extraordinary resilience, a relic surface forged by eons in interstellar cold. Each gas bubble released beneath that crust would exert pressure locally, but the surrounding rigidity would distribute the stress evenly, preventing directional thrust. The result: a ghostly emission with no recoil, a comet that breathes without moving. Still, there remained one subtle clue. The brightness of 3I Atlas fluctuated rhythmically, not chaotically. Photometric data showed slight undulations with a period of around 16 hours, too long for noise and too regular for coincidence. Some interpreted it as a rotation signal, suggesting that the comet was indeed spinning and that its activity modulated with each turn. If that were so, the symmetry of outgassing might only be apparent over time, a dynamic equilibrium where thrusts in one direction were cancelled by those in another across the full rotation cycle. In that sense, the balance was not static but temporal, achieved through motion rather than stillness. This idea resonated with the deeper beauty of physics. Even equilibrium can be alive, maintained not by stillness but by rhythm. The comet's jets might flare and fade like alternating breaths, each pulse neutralized by the next. To a telescope integrating over hours, the average would appear steady, but beneath that calm was a world in motion, spinning through cycles of sublimation and repose. The absence of acceleration, then, was not a mystery. It was the sum of opposites perfectly phased. Yet the paradox persisted when compared to known comets. Even those with symmetric outgassing show measurable deviations. Why was 3I Atlas so different? The answer might lie in its heritage. Interstellar comets are forged in alien systems, where radiation, chemistry, and stellar winds differ profoundly from our sun's. The ice composition might include exotic volatiles with lower energy release, producing gentle thrust despite vivid brightness. Or perhaps the dust-to-gas ratio was unusually high, meaning most of the visible light came from heavy, slow-moving grains that contributed little to momentum transfer. Every hypothesis brought us closer to the same realization. The dynamics of 3I Atlas were teaching us that not all activity leads to motion. One scientist described it like this: "It's as if the comet whispers, but the cosmos never hears it. The gas and dust cry out into the vacuum, yet the nucleus drifts untouched, deaf to its own voice." The elegance of that image captured the spirit of the investigation. The absence of non-gravitational acceleration was not an absence of life, but a signature of balance, perhaps even a kind of perfection carved by cosmic time. Still, for the scientific mind, perfection invites suspicion. Could such balance be entirely natural? The thought lingered, unspoken in conference rooms and email threads. But the data, for now, gave no grounds for speculation beyond physics. The next step was clear: quantify the unseen forces by bounding them. If we could estimate the minimum mass required to keep the trajectory so pure despite the visible outgassing, we might reveal the true scale of this visitor. A heavier nucleus would imply an object of immense size, possibly tens of billions of tons. A smaller one would force us to confront new mechanisms of symmetry. Either way, the numbers would speak louder than wonder. And so the focus began to shift from motion to matter. What was the mass of 3I Atlas? How dense could an interstellar comet be? And how much material was it shedding as it approached the sun? The dynamics of recoil had led to a doorway, but behind it lay a deeper question of proportion: how the balance of light, dust, and gravity could coexist so flawlessly. That is where the next inquiry begins. Estimating the body's weight by measuring the light it loses, tracing the invisible link between brightness and mass, between what we see and what holds it steady. For only by understanding the substance of 3I Atlas can we know why it moves so little when it burns so brightly. And that is where the next chapter begins. If the comet's silence under thrust was to be believed, then its weight must be extraordinary. The only way for 3I Atlas to shrug off the subtle kicks of outgassing was if its mass, its sheer physical presence, was large enough to anchor it against the faint winds of sunlight. The question was, how large? In the cold language of physics, light can reveal weight, and brightness can whisper the story of hidden tons of material drifting unseen beneath a haze of dust. The astronomers now turned their gaze from motion to substance, from dynamics to density, searching for what mass could explain the impossible calm. Every comet glows not by its own power, but by the sunlight it scatters and re-emits. The brightness we measure is therefore a proxy for the total amount of material being liberated: gas, dust, ice grains, and fragments, all caught in the luminous fog of the coma. By studying that light across weeks and months, we can infer how much mass the comet is losing. For 3I Atlas, this record stretched from July through October of 2025, a period that included its peculiar tail reversal and its steady brightening toward the Sunday. When the data were integrated, the cumulative mass loss reached astonishing figures: millions of tons of material sublimated into space. This number, however, was only half the equation. What mattered more was what remained: the reservoir of matter that must still reside within the nucleus to maintain its shape and trajectory despite that erosion. To quantify this, Astronomers modeled the outflow as a continuous jet of gas escaping at several hundred meters per second. The recoil from that gas, if the nucleus were small, would have been enough to nudge its orbit perceptibly, yet the orbit held firm, implying a nucleus of at least tens of billions of tons. Translating that into size required assumptions about density, and here the uncertainties widened. Cometary densities vary wildly. Some, like 67P Churyumov-Gerasimenko visited by the Rosetta spacecraft, have densities barely above that of air, a loose lattice of dust and ice, porous as snow. Others, like Halley's comet, are denser, but still far from solid rock. If 3I Atlas had a density near 500 kilograms per cubic meter, consistent with a compact but icy interior, then a mass of 10 billion tons would correspond to a diameter of roughly 2 kilometers. But if it were more porous, perhaps closer to 200 kilograms per cubic meter, the size would have to be nearly 3 kilometers across. In either case, the object would be among the largest interstellar comets ever observed, rivaling even Hale-Bopp in volume. And yet, size alone could not account for its unusual behavior. Mass stabilizes motion, but it cannot explain the remarkable balance of its jets. So the researchers sought evidence in its luminosity curve, how its brightness rose and fell with proximity to the Sunday. By comparing the rate of brightening to empirical models from known solar system comets, they could estimate not just the total amount of material lost, but also the efficiency of its sublimation. The results hinted at something unexpected. The comet's activity level was modest compared to its size. It was large, but not explosively active. Its dust production rate was roughly that of a medium-sized comet, yet it remained visually brilliant because its coma particles were unusually reflective, perhaps coated with fresh frost or crystalline ice. This subtle detail shifted the interpretation. If 3I Atlas's surface was shedding bright but lightweight grains, the visual brightness would exaggerate the true mass loss. That meant the real rate of erosion might be lower than initially thought, strengthening the case for a massive core. In other words, the comet might be an enormous object, leaking only gently, a giant whispering through frozen breath. To put this in context, scientists turned to familiar yardsticks. Halley's comet, with its 11-kilometer nucleus, has a mass of roughly 200 billion tons. Hale-Bopp, nearly twice as wide, exceeds 1 trillion tons. 3I Atlas, even at the lower estimate, would fall in the range of tens of billions, placing it squarely between these two icons. That scale alone was sufficient to neutralize most outgassing effects. If a few million tons of gas escape over several months, the fractional change in momentum becomes microscopic, a statistical tremor lost in the symphony of orbital mechanics. But there was a deeper consequence to such mass. Interstellar comets are not eternal wanderers. They are relics of ancient planetary systems, ejected long ago through gravitational slingshots. For one to survive millions of years, adrift between stars without disintegrating, it must possess structural integrity far beyond the fragile bodies that orbit our Sunday. A nucleus of this scale and density could indeed endure the interstellar void, its outer crust hardened by cosmic radiation, its interior locked in perpetual frost. 3I Atlas might therefore be more than a mere comet. It could be a fossil of another system's dawn, a survivor from an age when its parent star still glowed young. Still, the estimates carried uncertainty. The apparent brightness varied with the angle of sunlight, the reflectivity of the dust, and the size distribution of particles. A change in any of these factors could shift the mass calculation by an order of magnitude. Some astronomers cautioned that the object might be smaller and denser, instead, a dark, compact nucleus masked by reflective debris. Others argued for a layered structure, an outer mantle rich in volatiles that produced transient brightness spikes, overlaying a dense inner core that bore the true weight. The truth likely lay somewhere between those extremes. To test these ideas, observers relied on light-scattering models, mathematical tools that describe how dust grains of different sizes reflect sunlight. By fitting these models to the photometric data, they could infer the relative contribution of small versus large particles. The findings pointed to a population dominated by millimeter-sized grains, far larger than the submicron dust typical of solar system comets. Larger grains fall back toward the nucleus more readily and resist acceleration by radiation pressure, leading to a denser, more confined coma. This supported the impression of massiveness, not just in the nucleus, but in the gravitational field that could retain such material nearby. Another key came from thermal modeling. As sunlight warms a comet, the rate of sublimation depends on the surface area exposed and the depth of insulating dust layers. For 3I Atlas, the measured activity suggested that only a fraction of the surface was actively venting, perhaps less than 10%. The rest remained dormant, shielded by dust or sintered ice. That meant the overall sublimation rate, when averaged across the full body, was extremely low. A small comet with such modest activity would fade quickly from view. Only a large one could remain bright while releasing so little. The logic tightened. The mass must be great indeed. As the numbers converged, a picture began to form. The comet's nucleus was likely between 2 and 3 kilometers across, composed of layered ice and dust, weighing somewhere between 10 and 50 billion tons. It had been losing a few million tons of material over months, a minuscule fraction of its bulk. Its gravity, though weak by terrestrial standards, was enough to shape the near field of dust, creating an unusually compact halo. The combination of slow erosion, reflective grains, and massive inertia explained why 3I Atlas looked alive but moved like stone. Still, questions lingered. Could a body so large have formed in another star system's outer belt, and yet carry the volatile signature we saw carbon dioxide and water ice in near equal measure? Most interstellar models predict that objects ejected from their birth systems lose their lighter volatiles long before entering interstellar space. The presence of both CO2 and H2O in such balance implied either a recent ejection or a protective crust that sealed the inner layers against cosmic desiccation. If the latter, then the nucleus was not only heavy but ancient, its surface an archive of cosmic weathering, its interior a pristine vault of primordial chemistry. The implications stretched beyond one object. If 3I Atlas represented a common type of interstellar debris, then the galaxy could be filled with dormant giants, vast, slow-moving relics, invisible, until they wander near a star and flare to life for a brief cosmic moment. These travelers, massive enough to carry their silence across light years, might serve as archives of planetary evolution beyond our own solar system. Each one would be a messenger, not of chaos, but of endurance. And yet, endurance brings its own puzzles. The same inertia that keeps the orbit steady also resists fragmentation. For most comets, approaching the Sun means disintegration. Heat fractures the crust, vents burst, and the nucleus often splits. If 3I Atlas remains intact near perihelion, that too will speak volumes about its structure, whether it is a cohesive monolith or a rubble pile bound by weak gravity. Observers were already preparing for that test. By late October 2025, the comet would reach its closest distance to the Sun, and the instruments would record how its brightness, spectrum, and morphology changed hour by hour. A stable light curve would confirm its strength. A sudden flare might reveal internal collapse. Either outcome would tell us something profound about how matter holds together after 1 billion years between the stars. For now, the hypothesis of a colossal dense nucleus stood as the simplest explanation for its motionless grace. But simplicity in science is never final. It is a temporary resting place for the mind before the next question awakens. If mass explains stability, what explains transition? As the comet approaches the Sun, new layers of ice will sublimate, and the chemistry of its activity will change. Carbon dioxide will yield to water vapor, faint jets will become violent streams, the entire equilibrium may shift. Somewhere within that transformation lies the next key to its story. And so the focus turns once again from how heavy it is to how it breathes, from the balance of forces to the evolution of matter itself. The physics of sublimation is about to unfold in full, where frozen carbon gives way to water, and the comet's internal structure reveals its buried history. The great stillness of 3I Atlas, forged in weight, will soon meet the Sun's fire, and in that encounter we may finally glimpse what lies beneath its calm. And that is where the next chapter begins. As 3I Atlas moved closer to the Sun, the quiet equilibrium that had defined its journey began to shift. The frozen chemistry that had lain dormant beneath its ancient crust was stirring, and the comet was entering a phase of transformation that few interstellar travelers survive. Up to this point, its activity had been dominated by carbon dioxide, volatile, efficient, able to sublimate even in the distant chill beyond Mars. But now, as the sunlight intensified and temperatures climbed, another form of ice was waking beneath the surface: water. The changing balance between CO2 and H2O would not only alter the comet's brightness and color, but could also reshape its very behavior. The inversion of its tail, the pattern of its jets, the timing of its surges, all might find their answer in this subtle yet powerful phase shift between two kinds of frozen breath. In the deep cold of space, every molecule has its threshold. Carbon dioxide begins to sublimate, far from the Sun, at around -78 degrees Celsius, releasing invisible gas that carries small grains of dust along for the ride. Water, by contrast, requires much more heat. Its ice remains inert until the comet approaches within 2 astronomical units, where sunlight becomes fierce enough to melt its crystalline bonds. The result is a natural relay race between volatiles. CO2 takes the first leg, driving the comet's early awakening, then hands the baton to H2O, which surges as the Sun grows larger in the sky. This progression is not random. It is written into the layered structure of the nucleus itself. Imagine the body of 3I Atlas as an onion of frozen epochs. The outermost layers, exposed to the interstellar void for millions of years, have lost their lighter ices, leaving behind pockets of CO2 locked beneath a thin crust of refractory dust. Deeper down, where the Sun's heat has never reached, lie reserves of water ice mixed with silicate grains and organic compounds. As the comet drifts inward, the energy of sunlight seeps into these strata in waves. First the CO2 awakens, venting through ancient fissures and weak spots. Then, as thermal fronts move inward, the water layer begins to boil, forcing its way out with greater pressure and dragging heavier particles into space. It is at this boundary between the carbon dioxide era and the water era that the character of a comet can change dramatically. In the case of 3I Atlas, this shift may have played out precisely during the period when its tail reversed direction. Observations from July showed spectra dominated by carbon dioxide lines, while later data hinted at a growing presence of water vapor. The transition coincided almost perfectly with the weeks between the Hubble and Nordic images. If the CO2-driven jets were oriented differently from the new H2O vents, then the shift in composition could naturally lead to a change in the direction of ejection. In other words, the comet did not consciously turn, it evolved. The forces shaping it were written in the physics of its own melting, but this process is not smooth. When two volatile layers with different sublimation thresholds interact, pressure can build unpredictably. CO2 gas trapped beneath a semi-permeable layer of dust can form reservoirs that suddenly rupture once the heat reaches a critical depth. When that happens, entire patches of surface can erupt, spewing material at velocities exceeding 100 meters per second. The jets that follow carve new channels, expose fresh ice, and alter the local topography. Each eruption rewrites the comet's face. If 3I Atlas possessed multiple layers stacked like this, it might alternate between periods of calm and violent bursts, cycles that could explain the sudden inversion of its visible emissions. Thermal modeling supports this idea. When scientists simulated how heat propagates through a stratified nucleus, they found that temperature waves lag behind solar distance by weeks. As a result, a comet's maximum activity often occurs not at the closest approach to the Sun, but slightly afterward, when heat has penetrated deep enough to reach the volatile rich layers. The timing aligns beautifully with the observed delay between 3I Atlas's CO2 decline and its surge in H2O emission. It was not responding to distance alone, but to depth, to the slow diffusion of warmth through ancient ice. This notion of layered activation paints a more intricate picture of cometary physics. The nucleus is not a uniform ball of ice, but a geological archive, where each stratum corresponds to a different chapter of its formation. The upper layers, rich in carbon-based molecules, tell the story of its exposure to interstellar radiation. The deeper ones, dense with water and refractory dust, preserve the conditions of the nebula from which it was born. In transitioning from one volatile regime to another, the comet is effectively revealing its history in reverse order, shedding its outer heritage before uncovering the core of its being. To study such transitions is to watch time evaporate. Spectroscopy offers the most direct evidence of this unfolding. As the comet's composition evolves, the light it emits changes color. CO2-driven activity tends to produce a colder, bluish glow in infrared bands, while water-dominated emission introduces stronger features in the ultraviolet and visible range. By comparing spectra taken at different epochs, astronomers can trace how the balance shifts. For 3I Atlas, the prediction is clear. As it approaches the Sun, the spectral lines of CO2 should weaken, while those of H2O strengthen, a chemical heartbeat that matches the rhythm of its journey. When this pattern emerges, it will confirm that the tail reversal was not a geometric illusion, but a thermodynamic narrative written in gas and light. Yet there is something poetic, almost sentient, about this metamorphosis. The comet, long frozen in silence, begins to breathe heavier as it warms, exchanging the faint whisper of carbon for the vigorous exhalation of water vapor. The same substance that gave life to Earth becomes, in a sense, the voice of an interstellar visitor. Each molecule escaping into sunlight carries with it a fragment of another world's chemistry, a taste of a star that no longer warms it. The physics of sublimation becomes an act of memory. This transformation also reshapes the comet's mechanics. CO2 outgassing produces relatively gentle forces, as the molecules are light and diffuse. H2O, by contrast, creates denser, heavier jets with more momentum. As the water layer takes over, the balance of thrust across the nucleus changes. If active vents are unevenly distributed, the resulting torque can alter the rotation period, possibly even reorient the spin axis. Such feedback loops can drive complex behaviors. A jet exposes new ice, the comet spins faster, sunlight hits a different region, and another jet ignites in response. The dance of light and rotation becomes self-sustaining until the internal pressure finds equilibrium again. 3I Atlas may thus be not only changing chemically but dynamically, its rotation subtly modulated by the rhythm of sublimation. To probe this, astronomers monitor light curves for periodic fluctuations. A rotating nucleus with localized active regions will show small oscillations in brightness, corresponding to the rotation period. During the CO2 phase, these variations were faint, suggesting limited activity from the sunlit hemisphere. But as water took over, the amplitude increased, a sign that new, more directional jets were firing. This observation, if confirmed, would tie the comet's spin behavior directly to the shift in volatile chemistry. The comet would not just be reacting to heat, it would be responding through motion, evolving its entire state of balance. There is a beautiful symmetry in this process. The very substance that destabilizes the comet also reveals its stability. Water, when liberated, erodes the surface and alters momentum, yet it also provides insight into the comet's cohesion. If the nucleus survives the outburst without breaking apart, it means its internal structure is strong, its binding force is resilient. In this sense, the transition from CO2 to H2O is both a trial and a revelation, a test of endurance for a body forged in another system's dawn. Still, the story is not only about chemistry or physics, it is also about the boundary between known and unknown. The more we study interstellar comets, the more we realize how their behavior challenges the tidy categories we have built from our own solar system's examples. 3. I-Atlas's phase transition may be a window into a different kind of ice chemistry altogether, perhaps one formed under exotic conditions where carbon dioxide and water coexisted in composite crystals, or where metallic impurities altered their capsules. Thermal conductivity. These details are invisible from afar, but their signatures ripple outward in every plume, every shift in light, every whisper of gas that telescopes capture. By late October, when 3I Atlas sweeps near perihelion, this transformation will reach its climax. The Sun will pour energy into the nucleus at a rate thousands of times greater than during the discovery months. The CO2 that once dominated will fade into insignificance, replaced by roaring plumes of water vapor. If the models are correct, the comet will brighten sharply, its coma expanding like a veil of diamonds in sunlight. But the risk will rise too. Water sublimation, with its greater energy release, can fracture the crust, splitting the nucleus into fragments. Whether the comet holds together or shatters will reveal how deeply the layers are bound. Either outcome will tell us something about the architecture of interstellar matter, how it builds, endures, and unravels, and when that moment comes, the instruments will be ready. Spectrographs will dissect its light, searching for the expected crossover point where CO2 lines fade and H2O peaks. Infrared telescopes will measure the heat signature of the coma, mapping how thermal energy flows through the dust. Polarimetry will reveal how the new jets scatter sunlight, exposing the texture of the evolving grains. Together, these measurements will let us listen, in the language of physics, to the sound of an alien world melting. For now, though, the picture remains incomplete, a transition caught mid-sentence. The comet has not yet spoken its final word, and beneath its glowing exterior, deeper changes are brewing. The activation of water ice is only the beginning. As the sun's warmth reaches further inward, heavier materials, dust, refractory minerals, complex organics will start to dominate the outflow. The composition of the tail will shift again, and with it, the patterns of light and motion will evolve into new forms. To understand this next stage, we must look beyond the chemistry of gas and into the behavior of solid dust, the way light scatters, the way particles drift, and the way perception itself can turn matter into mirage. And that is where the next chapter begins. As the inner layers of 3I Atlas began to breathe, the transformation did not stop at gas. With each surge of water vapor, new torrents of dust followed grains and fragments that had slept for millions of years, now awakened by sunlight. These particles, suspended in the vast exhalation of the comet, became the storytellers of its evolving nature. Unlike gas, which follows the logic of thermodynamics and chemistry, dust is ruled by light itself. Every particle, no matter how small, is caught in an invisible tug-of-war between gravity and radiation. It is in this subtle battlefield that the next mystery of 3I Atlas unfolds. How the size of its dust, grains, and the way they scatter light could sculpt illusions across the sky and make the comet appear to defy physics. Radiation pressure is one of the gentlest yet most persistent forces in the cosmos. It comes not from the heat of the sun, but from its light photons that strike particles and push them outward. For large objects like planets, this pressure is negligible. But for dust grains, especially those smaller than a few micrometers, it can be decisive. To describe this interplay, astronomers use a dimensionless parameter called the beta factor, which compares the force of sunlight to that of solar gravity. A grain with a beta close to 1 is almost weightless under gravity. Sunlight pushes it away as strongly as the sun pulls it in. A grain with a very small beta, by contrast, is heavy enough to follow the comet's orbit faithfully, only slightly disturbed by light. The behavior of an entire comet's tail, its shape, direction, brightness, depends on how these countless grains distribute along that spectrum. For 3I Atlas, this relationship proved crucial. When the water sublimation phase began, the outflow of dust intensified, but the visual pattern of the tail became stranger. Observations showed streaks of material that seemed to align not perfectly opposite the sun, as radiation pressure would dictate, but slightly skewed, almost following the comet's orbital path. Some astronomers suspected that the tail was composed predominantly of large grains, ones with very low beta values, which remain gravitationally bound to the nucleus. Such heavy particles move slowly, tracing elegant arcs rather than streaming directly away. When viewed from Earth, these arcs can appear as straight lines pointing sunward, a trick of geometry that mimics an anti-tail. This interpretation, however, introduced its own puzzles. The optical properties of the tail did not match the dull red hue expected from large dust grains. Instead, its brightness suggested smaller particles, those that scatter light more efficiently and often produce a bluish tinge. To reconcile this, researchers proposed a dual population: large, dark grains forming the skeletal structure of the tail, and small, icy ones floating above them, catching sunlight like frost on glass. The interaction between these populations could produce the peculiar glow that made 3I Atlas so visually deceptive. In one direction, massive grains curved gently along the comet's orbit, while in another, micrograins reflected sunlight forward, creating the illusion of a narrow beam pointing toward the observer. The interplay of light and matter in this context is almost painterly. The dust does not simply reflect sunlight, it redirects it, polarizes it, and sometimes enhances it in specific directions, depending on size and composition. Small grains, comparable to the wavelength of light, scatter most strongly at angles near 90 degrees, creating halos and asymmetries. Larger grains act like tiny mirrors, producing forward scattering peaks that brighten the region facing the sunday. This means that a comet observed from Earth, near opposition, can show a sunward glow even when all material is physically moving away. The comet is not misbehaving, the light is. Polarimetry, the study of how light's orientation changes when scattered, offers a way to untangle this illusion. When light bounces off dust grains, it becomes polarized. Its waves align in specific directions. The degree of polarization depends sensitively on particle size, shape, and composition. By measuring how polarization varies with the comet's phase angle, the angle between the Sun, the comet, and Earth, astronomers can infer the dust's characteristics. For 3I Atlas, early polarimetric data hinted at low polarization at small phase angles, rising steeply as the angle increased. This pattern suggests a mixture of compact refractory grains and fluffy aggregates coated with volatile ice. Such a combination can create both high reflectivity and complex scattering effects, explaining why the comet's brightness sometimes peaked in unexpected directions. But beyond the physics, there is a kind of quiet poetry in this. Each grain of dust is a fragment of another solar system, a relic of cosmic construction. When sunlight touches it, the grain becomes a messenger across space and time, translating the energy of one star into the story of another. The color, the polarization, the brightness, They are not just measurements, they are signatures of origin. In the case of 3I Atlas, the peculiar scattering behavior might not only tell us about its dust size, but also about its birthplace. If its grains are unusually large and compact, it may have formed in a dense, cold disk where collisions fused particles early. If they are fragile, porous, and coated with volatiles, it may hail from a gentler, more diffuse region where ice and silicates interwove delicately. As the comet continued its march toward perihelion, the structure of the tail became increasingly layered. Spacecraft tracking and ground-based telescopes revealed faint striations bands within the dust plume, likely corresponding to separate outbursts or shifts in emission. Each layer carried its own grain size distribution, its own beta signature. The oldest material, released during the CO2 phase, consisted of coarser, slower-moving particles that trailed closely along the orbital path. The newer material, driven by water vapor, included finer dust accelerated more quickly by sunlight. Together, they formed a composite structure, a thin, sharp inner spine surrounded by a broader, fan-shaped envelope. Seen from Earth, the overlap of these components could easily create the impression of multiple tails or apparent reversals. To the human eye, such complexity evokes wonder. To physics, it is a symphony of forces: gravity, radiation, rotation, and time, each playing its note. Dust grains, though tiny, obey cosmic choreography. When ejected, they begin a journey governed by equations that balance light pressure against gravitational pull. The smallest particles, barely a fraction of a micron, are quickly blown away, forming wide, diffuse halos that catch starlight. Medium-sized grains linger, tracing graceful curves that mark the recent history of outgassing. The largest ones, stubborn and heavy, hover near the nucleus like satellites, slowly falling behind as the comet races ahead. These overlapping populations blur into a single luminous tapestry when seen across the vast distance between worlds. For 3I Atlas, this dance is further complicated by its interstellar pedigree. The dust it carries is not like the dust of our solar system. Its optical constants, how it reflects, absorbs, and transmits light, may differ because of its exposure to cosmic rays and interstellar radiation fields. Over millions of years, those exposures could have altered the surface chemistry of each grain, coating them with organic crusts, or transforming crystalline ice into amorphous glass. Such changes affect how the dust interacts with sunlight, particularly in polarization and color. If this alien dust has a unique refractive index or roughness, it could produce the uncanny scattering features that puzzled observers. What we perceive as a strange orientation of the tail might, in fact, be the fingerprint of another star's dust. The importance of distinguishing between physical and optical phenomena cannot be overstated. The human brain, evolved under one sun and one set of skies, is easily misled by light's subtleties. When we look at 3I Atlas and see a tail seemingly pointing toward the sun, we are witnessing a collision between perception and physics. The comet is not breaking rules, it is teaching us how fragile our intuitions are in the cosmic scale. By decoding its scattered light, we are learning to see not with expectation, but with analysis. To move beyond appearance, astronomers are preparing coordinated observations, combining photometry, polarimetry, and spectroscopy. Photometry tracks brightness over time. Polarimetry deciphers particle properties. Spectroscopy reveals composition. Together, these tools can reconstruct the three-dimensional structure of the dust cloud. By modeling how different grain sizes move under radiation pressure, scientists can simulate what the comet should look like from various viewing angles. Comparing those models to real images allows them to isolate which features are genuine and which are projections. This process transforms illusion into knowledge, light into geometry. But the implications of these findings go further than one comet. Understanding how light interacts with dust from another star helps refine how we interpret exoplanetary disks, protoplanetary clouds, and even interstellar extinction, the dimming of starlight as it passes through cosmic dust. 3I Atlas is not only a traveler, it is a calibration tool, a laboratory drifting through space. Each reflection, each scattering, pattern, helps anchor our theories of how matter behaves beyond the sun's reach. As the comet's water-driven activity intensified, the dust composition continued to evolve. Refractory grains, made of silicates and carbonaceous material, began to dominate over volatile ice particles. This shift would soon change not only the tail's brightness, but also its structure and color. As more solid material escaped, radiation pressure would exert stronger influence, pushing finer dust into broader fans, while heavier fragments clung close to the orbital plane. The phase of light-driven illusion was giving way to one of dynamic transformation, a stage where the physics of dust motion would intertwine with the rotation of the nucleus itself. Soon, the focus would no longer be on how the comet looked, but on how it moved. The alternation of active regions, the rhythmic pulse of jets turning on and off with each rotation, would start to reshape the entire morphology of the tail. What appeared as stable beauty would reveal itself as a complex, living cycle. To understand that evolution to trace how light gives way to motion, we must follow the story, from the scattering of dust to the rhythm of rotation, from the illusion of brightness to the heartbeat of spin. And that is where the next chapter begins. As the veil of dust thinned and sunlight reached deeper into the spinning body of 3I Atlas, astronomers began to notice something subtle but persistent: a rhythm. The brightness of the comet, when plotted over hours and days, was not smooth. It pulsed, rising and falling like a breath. The pattern repeated with uncanny regularity, hinting at a rotation hidden beneath the chaos of light. It was as though the comet, after billions of years adrift between stars, was turning slowly in the sunlight, revealing and concealing its scars in a measured dance. From this rhythm emerged a new layer of understanding, that the strange shifts in tail direction, the uneven brightness, the flickering jets, might not be random eruptions at all, but the consequence of a rotating, uneven world, a nucleus alive with alternating zones of activity. Comets, though often imagined as homogeneous snowballs, are rarely uniform. Their surfaces are mosaics of contrast. Some regions dark and crusted with carbon-rich dust, others bright with exposed ice. When sunlight strikes one hemisphere, volatile material heats, sublimates, and vents outward, creating localized jets. Meanwhile, the shadowed side cools and falls silent. As the nucleus spins, the cycle repeats, with one set of vents extinguishing as another ignites. Over time, this process etches distinct terrains into the surface, carving pits, ridges, and cavities that serve as conduits for future activity. For 3I Atlas, these alternating active regions may hold the key to its perplexing behavior. The reason its emissions appear to reverse, why its coma brightens in waves, and why no single model of sublimation can fully capture its motion. Data from similar comets within our solar system provide a precedent. The Rosetta mission revealed that Comet 67P's jets originate from discrete vents, many of them clustered near cliffs or depressions, where sunlight can strike at shallow angles. As the comet rotated, the illuminated vents alternated, causing both the direction and strength of outgassing to change cyclically. From Earth, such changes would appear as oscillations in tail structure and brightness, even if the underlying motion were perfectly periodic. 3I Atlas, too distant for direct imaging of its surface, exhibits these same telltale signatures, short-term fluctuations in brightness, repeating every 16 to 20 hours. Superimposed on its long-term increase in activity, the rotation itself may not be fast. Interstellar comets, forged under alien suns and ejected into the void, tend to spin slowly, their angular momentum damped by eons of isolation. Yet even a slow rotation, when paired with asymmetric outgassing, can shape the comet's entire appearance. If one vent on the northern hemisphere releases water vapor, while another on the southern side emits CO2, the alternating exposure to sunlight could cause the jets to swap dominance every half rotation. From our vantage point, the tail's direction would seem to flip a geometric echo of the nucleus's internal rhythm. What first appeared as a sudden inversion could thus be the visual signature of a rotating world, balancing light and shadow across its fractured surface. Such behavior also explains the timing of its transformation. The change between carbon dioxide and water vapor activity did not happen all at once, but gradually, through alternating phases of vent illumination. Each rotation brought the sun's rays to a slightly different angle, warming one region while cooling another. Over days, the cumulative heat spread deeper, and the cycle of dominance shifted from CO2 jets to H2O plumes. The comet was not switching personalities, it was evolving through rotation. Yet the rotation of 3I Atlas is not merely a passive motion, it is an active participant in shaping its destiny. Every jet that erupts from its surface exerts a torque, a tiny twist that either accelerates or decelerates its spin. Over time, these torques can alter the period dramatically. A vent near the equator, firing consistently, might speed up rotation, while one near the pole could slow it down. If multiple vents operate at once in opposing directions, they could create complex precession effects, causing the spin axis to wobble like a top. For an object crossing the solar system only once, such changes happen quickly, compressed into the brief window of its sunlit passage. The result is a feedback loop. Sunlight drives jets, jets change spin, spin changes which regions receive sunlight, and the pattern of activity evolves anew. This dance of cause and effect manifests in the comet's shape and structure. As the spin axis shifts, new cracks form, old vents collapse, and fresh areas of ice become exposed. Observers tracking the light curve can watch this evolution unfold in real time. The periodicity, stretching or shrinking slightly, the amplitude of brightness variations growing as new jets ignite. For 3I Atlas, these nuances are more than curiosities. They are fingerprints of internal change. By mapping how the light curve fluctuates before and after perihelion, scientists hope to infer whether the nucleus is gaining or losing rotational speed, and thus whether the torques are balanced or asymmetric. The prospect of asymmetric torque carries profound implications. If one hemisphere of the comet consistently dominates, the accumulated spin-up could eventually tear the nucleus apart. We have seen this fate before. Comet Ison in 2013 fragmented catastrophically near perihelion, its nucleus unable to withstand the rotational stress from asymmetric jets. Should 3I Atlas follow a similar trajectory, it might disintegrate in a spectacular display, its fragments tracing spirals through space, each carrying a memory of the parent's final rotation. But if the nucleus endures, maintaining equilibrium between opposing jets, it would reveal a remarkable structural resilience, a hint that its interstellar origins endowed it with unusual cohesion. To test these possibilities, astronomers rely on high-precision photometry. Each pulse of brightness can be converted into a point on a rotational phase curve, revealing the periodic rhythm of the nucleus. If the period changes measurably over weeks, it signals ongoing torque. For now, the data suggest a modest but stable rotation, perhaps around 18 hours per cycle, with minor drift just enough to produce the observed alternation of activity. The shape of the light curve, with two peaks of unequal height, hints at an elongated or irregular body, perhaps a contact binary like 67P, or a lumpy fragment, resembling 2I Borisov. Such shapes naturally lead to uneven heating, further reinforcing the cycle of active and dormant regions. The implications extend beyond mere geometry. A rotating nucleus that alternates between active regions can explain nearly every puzzling feature seen so far. The anti-tail observed by Hubble may correspond to one hemisphere's vent firing as it rotated into sunlight, releasing larger grains that followed the orbital plane. Weeks later, as the opposite side became dominant, finer dust, driven by water vapor, jets would form a conventional tail pointing away from the Sunday. The inversion, then, was not a contradiction of physics, but a synchronization of spin and light, a celestial choreography between day and night on an alien world. But beneath the elegance lies tension. Rotation, once altered, seldom returns to balance. If 3i Atlas is indeed spinning unevenly, it may be precessing a slow wobble of the axis caused by off-center jets. Such precession can modulate the periodicity of its activity, turning a simple rhythm into a layered symphony of beats. Observers might detect secondary cycles, perhaps every few days, superimposed on the main rotation. These cycles would correspond to shifts in the direction of the spin axis, subtly altering the angle of solar illumination, and thus the strength of each jet. Capturing these patterns would offer a rare glimpse into the internal mechanics of an interstellar body, how its fractures, cavities, and asymmetries conspire to shape its behavior under starlight. The study of these cycles also opens a philosophical window into the nature of change itself. What we see as randomness, flares, reversals, brightening is, on closer inspection, the predictable heartbeat of a rotating system responding to external energy. The comet's apparent chaos hides a deep order, a self-regulating pattern written in the language of rotation and sunlight. It is a reminder that even in the cold, indifferent expanse, between stars, order can emerge from simplicity and rhythm from ruin. Still, many questions remain. If the active regions alternate predictably, why do some emissions appear to persist even when their hemisphere should be in shadow? Perhaps the heat conducted through subsurface layers keeps the gas flowing for hours after local sunset, like embers glowing beneath ash. Or perhaps some vents are positioned near the poles, where illumination is more continuous, blending day and night into a single eternal dawn. The geometry of such activity could explain why 3i Atlas's brightness never fully fades between pulses. It is never entirely asleep, only resting between breaths. As perihelion approaches, the stakes of these dynamics grow. Increased solar heating will amplify all effects: outgassing, torque, spin-up, precession. If the balance holds, 3i Atlas will emerge brighter and more structured than ever, its jets painting spirals across the inner solar system. If it fails, it may fragment, scattering its layered story into dust. In either case, the key lies in monitoring its rotation, for that rotation is the comet's pulse, the measure of its internal life. And beyond the rotation lies the next horizon. The interplay between spin and sunlight will soon be tested not only by observation but by instrumentation, cross-referencing data from space-based telescopes, ground observatories, and infrared detectors to ensure that what we see is real and not artifact. The time is coming to measure, to verify, and to compare to separate nature's rhythm from the limitations of our own tools. That next phase, the calibration between human perception and cosmic truth, begins, where observation meets confirmation. And that is where the next chapter begins. In science, wonder must always walk beside verification. As the story of 3i Atlas unfolded across telescopes and theories, one truth remained constant. No discovery is real until the instruments agree. The images that had astonished the world, the tail that pointed the wrong way, the luminous jets that seemed to shift without warning, the rhythm of brightness pulsing through the void, were all filtered through the lenses, sensors, and atmospheres of our imperfect observation. To understand the comet's true nature, astronomers now turned from the poetry of motion to the discipline of method, from interpretation to calibration. The next step was to test every claim against the instruments themselves, to see whether what we thought we saw was written by the comet or drawn by the tools we used to observe it. Every telescope, no matter how advanced, is a storyteller with its own accent. The Hubble Space Telescope, orbiting above Earth's atmosphere, speaks in clarity and precision, capturing light uncorrupted by air. The Nordic Optical Telescope, resting under the thin skies of La Palma, sees through layers of air that dance with turbulence, distorting the light from distant objects. When both recorded 3I Atlas's changing tail, the contrast between their perspectives was both a gift and a challenge. If they agreed, the phenomenon would stand on firm ground. If they differed, the difference itself would become a clue. The process of cross-verification began in earnest. Astronomers compiled the Hubble data from July 21, 2025, the image that had first revealed the mysterious sunward emission, and compared it pixel by pixel with ground-based exposures taken in early August. The aim was not only to confirm the geometry but to test whether instrumental artifacts could mimic the observed features. The first step was to account for motion blur. Space telescopes track moving targets with sub-arc-second precision, but a slight error in the comet's velocity estimate can stretch or smear the coma, creating false linear features. By reprocessing Hubble's raw frames using updated orbital parameters, the team confirmed that the sunward plume was not a tracking artifact. It remained sharp even after correction, suggesting it was real. On Earth, the challenge was different. The Nordic telescope, though equipped with adaptive optics, still faced atmospheric scattering tiny fluctuations in air density that blur and elongate faint features. To rule out interference, astronomers used multiple exposures across different nights, stacking and rotating the images to remove background stars and cosmic rays. The result was consistent, a tail aligned in the expected anti-solar direction, contrasting with the earlier Hubble image. This confirmed that the reversal was not the product of atmospheric distortion. The instruments disagreed not because of error, but because the comet itself had changed. Still, to claim transformation, one must eliminate every systematic bias. The calibration continued. Image processing pipelines were tested under blind conditions. Simulated comet data with known geometries were fed into the algorithms to see if they could reproduce false anti-tails. None could. The direction of the sunward plume in Hubble's data resisted all attempts at reinterpretation. Meanwhile, spectroscopic data from smaller observatories in Chile and Hawaii showed that CO2 emission lines peaked precisely during that same period, fading as water lines rose weeks later. The spectral transition matched the visual one, tying the tail inversion to a physical process rather than a quirk of perspective. But even as consensus grew, doubt remained a necessary companion. Astronomers understand that instruments are extensions of the human eye, and therefore of human limitation. Light is easily deceived by glare, diffraction, or data reduction techniques that smooth and sharpen the world according to our expectations. To counter that, a parallel effort emerged to involve multiple observatories across different wavelengths. Optical data were only one layer of truth. Infrared observations could see the heat of the dust, revealing whether the bright plume corresponded to warm material or cold reflective ice. Radio telescopes could detect gas directly, tracing molecules invisible to light. And if fortune allowed, the James Webb Space Telescope, with its unparalleled sensitivity to infrared spectra, could probe the comet's chemistry in exquisite detail, measuring the ratio of water to carbon dioxide as it evolved. The coordination of these instruments was a triumph of collaboration. From Chile's high-altitude domes to Canary Island summits, from orbiting telescopes to citizen astronomers with backyard equipment, the network of watchers formed a living chain of evidence. Each node added resolution to the puzzle. Each wavelength spoke a different dialect of the same truth. When the data were layered together, they painted a picture more intricate than any single instrument could reveal. The comet's apparent contradictions began to align into harmony. One lesson became clear: the universe rarely lies, but our methods sometimes whisper half-truths. Atmospheric seeing, for instance, can smear a faint, thin dust filament into an apparent solid beam. Detector nonlinearity can exaggerate brightness contrast near the nucleus, making a subtle gradient look like a sharp edge. Even the algorithms that subtract background stars can accidentally carve artificial structures into the image. To guard against such ghosts, teams developed independent pipelines, each designed with different assumptions, then compared results blindly. When all converged on the same morphology, confidence grew. Yet verification is not only technical, it is philosophical. To verify a discovery is to confront our own faith in perception. In a sense, calibration is the act of humbling our instruments before nature, admitting that precision is not certainty. The astronomers working on 3i Atlas approached this task with that humility. They did not rush to proclaim miracles, they sought consistency. The phrase that circulated among them was simple: if it is real, it will reappear. And it did. As September advanced, telescopes across both hemispheres caught the comet's tail evolving again. The direction of emission stabilized, pointing firmly away from the sun, and the spectral signature confirmed the dominance of water vapor. The earlier sunward feature had vanished, just as a physical transition model would predict. Nature had performed its experiment twice, once in light, once in chemistry, and both pointed to the same conclusion. Still, cross-verification did more than confirm a single event. It exposed the fragility of our interpretations and reminded researchers that every measurement is a conversation, not a proclamation. For instance, when comparing Hubble and ground data, astronomers noticed a subtle discrepancy in the brightness of the outer coma. At first, it was attributed to differences in exposure and sensitivity. But deeper analysis revealed that Earth's atmosphere was absorbing certain wavelengths from sodium and oxygen emissions, faint lines that space-based instruments could see clearly. This discrepancy, once accounted for, revealed something new. 3i Atlas was emitting neutral sodium, a marker of intense heating near active vents. What began as a correction turned into discovery. This principle, the transformation of error into insight, became the guiding spirit of the project. Even imperfections carried meaning. The slight trailing in ground-based images, for example, hinted at the speed of dust particles relative to the comet's core. The subtle differences in coma color between instruments pointed to variations in grain size and composition. Each inconsistency, when studied closely, revealed another facet of truth. The comet was not merely a celestial body to be measured. It was an instrument itself, a mirror through which the precision of our science was tested. As the observational campaign expanded, the question of reproducibility grew. Could amateur astronomers detect the same features using smaller telescopes? Surprisingly, yes. Around the world, skilled observers with 30-centimeter telescopes captured faint hints of the asymmetric coma. Their data, processed independently and compared against professional images, matched the general shape and timing of the transitions. It was a quiet victory for citizen science, a demonstration that the cosmos does not belong solely to billion-dollar observatories, but to anyone patient enough to watch. Through this cooperation, the community learned a profound lesson about trust and skepticism. Verification does not mean doubting reality. It means giving reality room to speak in more than one voice. Each instrument, from the smallest lens to the mightiest mirror, hears a different octave of the universe's music. Only by layering them together can we hear the full chord. The verification of 3i Atlas's phenomena was therefore not just a test of data, it was an act of orchestration. But even this symphony of confirmation carried reminders of limitation. Instruments are not immune to fatigue. Detectors age, calibration drifts, atmospheric transparency fluctuates with the weather. To sustain long-term accuracy, teams had to recalibrate regularly, pointing their instruments at known stars or standard comets. This process consumed time, but ensured that the brightness of 3I Atlas could be compared consistently across months. Without it, an illusion of variability could easily emerge where none existed. The ultimate goal was to ensure that every claim about the comet, its rotation, composition, changing jets, rested on a foundation of reproducible evidence. When the instruments finally spoke in unison, a coherent story emerged. The sunward plume was real and transient, the subsequent reversal was genuine. The spectral transition confirmed physical evolution. The data did not contradict each other. They complemented one another, revealing different chapters of the same narrative. 3I Atlas was not an illusion, but a dynamic system, obeying the laws of thermodynamics, geometry, and rotation. And yet, just as certainty seemed within reach, another layer of complexity surfaced. During the September-October window, faint discrepancies appeared between observatories in the northern and southern hemispheres. The angle of observation relative to the comet's orbital plane differed slightly, and so did the appearance of the tail. In some images, the coma looked symmetric, in others, lopsided. It became clear that even truth has perspective, that the same object, viewed from different latitudes, could reveal different facets of itself. The comet was both constant and changing, depending on where one stood. This realization set the stage for the next challenge, not just to confirm what we saw, but to synthesize all viewpoints into a unified model. To do that, astronomers needed to track the comet across multiple vantage points, even beyond Earth if possible. Mars, which the comet would pass near in early October, offered a rare opportunity. Orbiters circling the red planet could photograph 3I Atlas from a completely different angle, free of Earth's atmospheric limitations. If successful, those observations would serve as the ultimate cross-check, a second planet, confirming what the first had seen. The anticipation was palpable. For the first time, two worlds might witness the same interstellar visitor from opposite sides of the Sun, comparing notes like scientists across the cosmos. And as the date of the Mars flyby approached, the community prepared to shift its gaze once more, not only to verify, but to expand the field of vision itself, to see through new eyes what no single world could see alone. And that is where the next chapter begins. As October approached, anticipation spread across observatories on two worlds. For the first time in human history, an interstellar visitor would be seen not only from Earth but from Mars as well. The geometry was extraordinary. 3I Atlas was set to pass near the Martian orbit on October 3, 2025, only weeks before its closest approach to the Sunday. This brief alignment offered a natural experiment that no human could have designed. Two vantage points separated by nearly 100 million kilometers, both staring at the same cosmic traveler from different sides of the solar system. From Earth, astronomers prepared to capture the familiar optical and spectral signatures. From Mars, orbiters equipped with cameras and spectrometers readied themselves to catch a second angle, one untouched by the distortions of Earth's atmosphere. It was as if the universe had arranged a calibration baseline across planets, allowing us to test, at last, whether what we thought we saw from one world truly matched reality from another. The Mars orbiters, especially the ExoMars Trace Gas Orbiter and NASA's MAVEN spacecraft, were given updated pointing instructions weeks in advance. Their instruments, designed to study the thin Martian atmosphere, could also detect faint dust and gas emissions in the surrounding sky. When 3I Atlas entered their field of view, even a few minutes of observation would suffice to reveal the direction of its tail and the ratio of gases in its coma. Meanwhile, from Earth's side, the Hubble Space Telescope and a global network of ground-based telescopes would continue their campaign, ensuring that every observable parameter, brightness, spectrum, polarization was recorded at overlapping times. The goal was synchronization, a cosmic stereo vision that could turn uncertainty into depth. When the Mars data finally began streaming down, the The first images caused a ripple of excitement. The tail was visible, faint but distinct, extending in a direction consistent with solar radiation pressure. No anti-tail appeared from this angle. To Martian orbiters, the comet looked perfectly normal, a sunlit head with a trailing plume, receding from the Sunday yet on Earth. Just days earlier, observers had reported subtle asymmetries, a flicker of brightness on the sunward side. This discrepancy was gold. It confirmed what the geometric models had predicted. That viewing angle could accentuate or erase the illusion of reversal. From Mars, the line of sight intersected a thinner slice of the dust sheet. From Earth, it passed nearly edge-on through it, amplifying the brightness of the overlapping layers. The mystery of the anti-tail was not entirely solved, but it was finally framed within perspective, geometry, and timing, a harmony of cause and observation rather than contradiction. With the Martian crosscheck complete, focus shifted to the next critical milestone, perihelion, on October 29, 2025. By then, 3I Atlas would be receiving over 10 times the solar energy it had during discovery, and the dormant layers of its nucleus would be awakening in full. Predictions diverged. Some expected a surge in brightness as new vents opened and water sublimation peaked. Others warned that the thermal stress might tear the nucleus apart. The case of Comet Ison in 2013 haunted every discussion. It too had brightened spectacularly before disintegrating near the Sun, leaving only a ghostly arc of dust behind. Whether 3I Atlas would endure or succumb was not just a matter of curiosity. It would determine whether we could study its evolution after perihelion, or only its remnants. Days before the close approach, solar observatories such as SOHO and the Solar Orbiter were brought into coordination. Their coronagraphs, designed to block the sun's glare, would watch as the comet skimmed through the inner solar system. From Earth's ground-based instruments, direct observation would be impossible during solar conjunction. The comet would vanish behind the sun's brilliance. The task, therefore, fell to space-based sentinels, whose instruments could track it continuously as it crossed the sun's vicinity. Data relay schedules were adjusted, filters recalibrated to handle the anticipated brightness spikes. This coordination transformed the perihelion passage into a planetary-scale experiment, merging heliophysics and interstellar science in one event. When the moment arrived, the first frames were almost theatrical. On October 29, a slender arc appeared in SOHO's coronagraph imagery, a luminous thread entering the field of view from the left. Over the next 24 hours, its brightness swelled by nearly a factor of 4. The coma expanded rapidly, developing a fan-like shape with a sharp leading edge. Then, just as suddenly, it began to fade. By October 31, the head had dimmed, replaced by a diffuse, elongated streak. No distinct fragments were visible, but the light curve suggested either partial fragmentation or the ejection of large amounts of dust that temporarily obscured the core. Infrared data from Solar Orbiter indicated intense water vapor emission during the peak, consistent with the final, violent phase of sublimation. Despite the ambiguity, the object survived. When it re-emerged from behind the Sun in early November, telescopes on Earth caught it again, faint but intact. Its brightness was lower than before, suggesting that a significant fraction of volatile material had been lost, yet its trajectory remained stable. No measurable non-gravitational acceleration appeared in the orbit calculations. This was crucial. If the comet had fragmented into smaller pieces, the gravitational model would have failed, showing tiny deviations. The absence of such deviation implied that even after its fiery encounter, the main body held together, a stoic survivor of stellar proximity. Now the stage shifted once more, toward the Earth approach scheduled for December 19, 2025. This would be the closest pass of its journey within observational reach, not only of the world's great observatories but also of small research stations and advanced amateurs. At that point, 3I Atlas would be less than a third of an astronomical unit from Earth, its coma wide enough to fill several arc-minutes in the night sky. Spectrographs could finally dissect its light with unprecedented precision. For weeks, astronomers had prepared target plans to capture every emission line from sodium to cyanide, from hydroxyl radicals to metallic traces. The data gathered during this window would complete the arc begun months earlier, connecting the story of gas, dust, motion, and heat into one continuous record. What made this phase especially valuable was its geometry. After perihelion, the comet's trajectory curved inward relative to Earth's orbit, placing it in a configuration ideal for measuring any subtle deviations from pure gravity. The precision of these measurements would depend on radar tracking and optical astrometry, both reaching accuracies of tens of meters per second. If any non-gravitational acceleration persisted, perhaps caused by asymmetric jets still active beneath the crust, it would appear here as a minute drift in the predicted position. To detect it, observatories across continents synchronized their timing systems to within milliseconds, feeding positional data into a shared pipeline. It was a global choreography of measurement, as meticulous as any cosmic ballet. December nights brought the culmination of the project. Observers reported that the comet's tail, though fainter, was more stable than ever. No new inversions, no sudden flares. Spectral data showed a steady decline in water vapor and an increasing dominance of refractory dust emissions. The chemistry was cooling. The nucleus was likely sealing itself, building a crust of silicates and carbon compounds that would preserve its interior for the long interstellar voyage ahead. For a moment, the comet seemed to rest a traveler, pausing before fading back into darkness. And yet, even in its quiet phase, it continued to teach. The approach provided the sharpest constraints yet on its mass and density. By comparing observed brightness decline with modeled sublimation rates, researchers inferred that the nucleus might have lost only a thin surface layer, perhaps a few meters deep. This confirmed its resilience and supported the hypothesis that interstellar comets possess hardened crusts shaped by eons of radiation exposure. Unlike the porous snowballs of our solar system, they are compact, ancient relics forged in alien suns and tempered by the vacuum between stars. The Earth approach also allowed high-resolution spectroscopy to probe trace elements rarely seen before. Sodium and magnesium emissions, faint during earlier phases, now stood out clearly. These signatures suggested that the comet's crust contained silicate minerals similar to those found in meteorites. The isotopic ratios hinted at an origin around a G-type or K-type star, not vastly different from our Sun, a sobering reminder that this object once orbited another sun-like world before being cast adrift into eternity. In its spectrum, we could read the echoes of a distant system, its chemical handwriting carried across interstellar space. But the most delicate test was yet to come, the measurement of post-perihelion acceleration. Over the weeks following its closest approach, positional data accumulated. When plotted against the purely gravitational model, a tiny residual emerged, a drift so slight it took days to confirm. The magnitude was on the edge of detection, but it leaned consistently in one direction, opposite the presumed dominant jet site. It was not enough to claim anything extraordinary, yet enough to remind scientists that the comet was not entirely inert. Some faint vent still whispered gas into the void, pushing imperceptibly against gravity. To interpret this subtle behavior, theorists began updating their thermophysical models. They simulated layered ice sublimation under the new crust, accounting for the thermal lag introduced by the material's altered conductivity. The results reproduced the small acceleration, confirming that even after its violent perihelion encounter, 3I Atlas remained alive, its heart still pulsing faintly beneath the skin of dust and rock. This realization gave the entire narrative a sense of closure. An interstellar body, battered yet intact, returning to the cosmic sea from which it came. carrying scars that would tell future travelers of its encounter with a yellow star and a civilization that watched, measured, and wondered. As December gave way to January, the comet faded from naked eye reach. Observations became sporadic, limited to large telescopes under pristine skies. The last confirmed detection showed it receding quietly into the outer dark, its brightness reduced by a factor of 10. It had given us nearly 6 months of mystery, debate, and revelation, a lifetime in the fast-flowing chronicle of astronomical discovery. But for scientists, the story was far from over. The data gathered from Mars, Earth, and solar orbiters would now be merged into a single coherent timeline. It would take months, perhaps years, to extract every pattern, every correlation. The observations were complete, but the interpretation was only beginning. And beyond the spreadsheets and equations, another thought lingered, a question that could not be answered by instruments alone. If an interstellar object could survive such a passage, carrying intact its chemistry and motion, how many others roam unseen, crossing the solar system in silence? How many stories like this drift past us each year, too faint to notice? The realization was humbling. The cosmos is not empty but filled with exiles, each a messenger from a distant world. And so, as 3i Atlas slipped beyond reach, attention turned to the horizon of possibility. The next chapter would not be about this comet alone, but about what comes after, about how we prepare for the next interstellar visitor, how we design instruments that can intercept it, how we refine our models to distinguish nature from the artificial, the ordinary from the extraordinary. The data had carried us to the edge of understanding. Now it was time to ask the harder question, the one that waits just beyond the glow of certainty. And that is where the next chapter begins. The departure of 3i Atlas marked more than the end of an encounter. It marked the beginning of a new age in how humanity looked outward. The comet had been both a mirror and a test, a mirror reflecting the limits of our understanding, and a test of how far our instruments, models, and imagination could reach. As it drifted beyond the reach of our telescopes, the data it left behind remained like an afterglow, a trail of numbers as faint and enduring as the dust it shed into sunlight. The next question no longer belonged to the comet itself, but to us. What would we do when the next visitor came? Would we merely watch again, or would we finally move to meet it? The lessons of 3i Atlas transformed every discipline that had touched it. Astrophysicists refined models of non-gravitational motion, learning how subtle outgassing could mimic artificial precision. Chemists revisited the limits of molecular endurance, asking how water and carbon dioxide could survive millions of years between stars. Even engineers, the ones who built the instruments that tracked it, began to think differently about readiness. If the first confirmed interstellar object, 1i Oumuamua, had passed too quickly for any interception, and the second, 2i Borisov, had been too faint for close study, then 3i Atlas had been the third and final warning. The universe was not a closed book. It was sending pages into our solar system, and next time we had to be ready to read one up close. Plans began forming before 3i Atlas even left the inner solar system. NASA's Planetary Defense Office and ESA's Comet Interceptor team convened joint workshops to assess the possibility of a standing mission, a spacecraft that would wait in space, fueled and dormant, ready to pivot toward the next interstellar arrival. The idea was simple in concept but revolutionary in execution. A permanent sentinel stationed near the L2 point, equipped with autonomous navigation and an onboard propulsion module capable of rapid acceleration. When an incoming object was detected, the craft would calculate a trajectory within days, initiate its burn, and intercept the visitor before it reached perihelion. It would not merely watch, it would meet. 3i Atlas provided the blueprint for what such a mission would need to see. Its brightness variations, composition transitions, and the fragile dance between gas and dust defined the instrumentation requirements. spectrometers sensitive across infrared and ultraviolet bands, cameras capable of polarimetric imaging, dust analyzers to capture and vaporize particles without destroying their isotopic fingerprints. Every lesson learned from months of remote observation was distilled into practical design, a way to turn the poetry of a distant traveler into a science of encounter. At the same time, theoretical physicists found themselves re-examining what natural meant. The trajectory of 3I Atlas had been consistent with natural forces, but its symmetry and mass stability had been eerily precise. A few speculative voices wondered aloud. Could some interstellar objects be fragments of technological origin? Not spacecraft in the cinematic sense, but remnants, probes, debris, relics of civilizations that, like us, once looked outward and sent emissaries into the dark. The idea was not embraced nor dismissed. It simply hung there, suspended between caution and curiosity, an open question for future instruments to test. Even beyond the halls of academia, something shifted. The story of 3I Atlas reached the public imagination in a way no comet had since Halley's return. News. Networks broadcast its glowing arc nightly. Artists painted it as a silver scar against the velvet of space. School children traced its journey in classrooms. The world saw, perhaps for the first time, that interstellar objects were not abstractions, but visitors quiet, passing messengers from other suns. The notion that our solar system was once again connected to others, not through signals or dreams, but through matter itself, ignited a subtle optimism. The vast distances between stars no longer felt like walls, but corridors. And as this sentiment grew, the science deepened. Radio telescopes scanning the path of 3I Atlas detected faint residual dust for weeks after its departure. The particles, moving slowly through the solar wind, carried distinct spectral fingerprints, silicates enriched with magnesium, organic molecules coated in frozen carbon. These traces suggested a complex chemistry, perhaps even more evolved than typical comets. Some researchers proposed that interstellar radiation had polymerized simple organics into long, chain-like molecules. In that sense, the comet had been a cradle of precursors, a frozen laboratory in motion. The notion that life's building blocks might drift between stars, carried by such messengers, no longer felt like a poetic metaphor, but an empirical possibility. Meanwhile, engineers revisited their models for detection. The existing survey systems, Pan-STARRS, Atlas, and the upcoming Vera Rubin Observatory, were powerful but reactive. They found comets weeks or months before perihelion, often too late for mission planning. What was needed was an early warning system for interstellar objects, a network of infrared telescopes at the edges of Earth's orbit, continuously scanning the inbound skies. Such a network could detect the faint heat of an object long before it reflected enough sunlight to be visible. The challenge lay not in technology but in commitment, in convincing the world that readiness for discovery was as vital as readiness for defense. Amid these plans, one quiet realization persisted. We had barely begun to understand the diversity of what drifted between stars. 3I Atlas had shown us a world of frozen volatiles, rich in gas and dust. 1I Oumuamua had been dry, tumbling, perhaps metallic. 2I Borisov had resembled a typical comet, yet with more pristine ices than any known in our system. The variety itself was the message. There was no single archetype of an interstellar traveler. They were as varied as the stars that birthed them. Some were relics of planetary collisions. Others were frozen embryos of worlds that never formed. Each was a fossil of cosmic evolution, a fragment of a larger story we were only beginning to read. By January 2026, the 3I Atlas archive was complete. Petabytes of data, cross-referenced across instruments and wavelengths, were handed to research groups worldwide. Among them, one analysis stood out, a reconstruction of the comet's origin. Using the chemical ratios and isotopic profiles, A consortium of astrophysicists traced its likely birthplace to a region of the galaxy, roughly 150 light-years away, a system near the constellation of Cygnus, where several young stars had recently formed planets. If the models were right, 3I Atlas might have been ejected from that system 500 million years ago, a byproduct of gravitational turbulence during planetary migration. It had travelled through interstellar space ever since, its path shaped by nothing but the faint pull of stars and the slow drift of galactic tides. And now, by chance or fate, it had wandered into ours. There was something profoundly human about that trajectory. A fragment cast out, drifting across the void, enduring storms of radiation and time, only to be noticed, studied, and understood by beings it could never know. It was, in a sense, a story of exile and return, not in the literal sense, but in the emotional resonance it carried. When astronomers spoke of 3I Atlas in conferences, they no longer spoke only in equations and reflectivity indices. They spoke of its endurance, its silence, its improbable survival. They spoke as if it had looked back. That emotion, though unscientific, became the seed of a larger vision. Plans emerged for the Interstellar Watch, a permanent network of observatories, spacecraft, and data systems dedicated to tracking and, when possible, reaching interstellar visitors. It was no longer enough to record them as curiosities. The next goal was contact, not in the sense of communication, but of proximity, to touch, to sample, to analyze at the atomic level, to hold in our instruments a piece of another star's history. In that pursuit, the memory of 3I Atlas would serve as both inspiration and warning. It had taught us that nature is capable of deception more elegant than imagination, that geometry can mimic intention, and light can lie more convincingly than words. It reminded us that even the most careful interpretation must bow to evidence gathered from more than one vantage point, and above all, it showed that discovery is not an act of conquest, but of humility. We do not uncover the secrets of the universe. We are invited to notice them, briefly, before they pass back into darkness. By spring of 2026, the comet was gone, invisible, unmeasurable, but not forgotten. Its coordinates lingered in databases, its lessons etched themselves into textbooks. Somewhere beyond Jupiter, it glided silently, cooling, coasting, slipping toward the outer edge of the heliosphere. Soon the solar wind would fade, and it would cross once more into the unbounded sea of interstellar space. The same radiation that had shaped it would once again claim it, polishing its surface, erasing the dust of its passage through our system. In 1,000 years, no trace of its encounter with Earth would remain except in our archives and in the questions it left behind. And one of those questions, quiet but persistent, had begun to echo through the halls of research, institutions, and agencies alike. What if next time the object does not merely pass through? What if one lingers, decelerates, or shows a pattern that cannot be explained by natural means? How would we respond? Would we recognize the difference between anomaly and intention, between a messenger of nature and one of intelligence? That question, whispered in both curiosity and unease, became the bridge to a new era of search, not for life as we imagine it, but for presence, however subtle, written in motion and light. And that is where the next chapter begins.